In the context of solving for the roots of nonlinear algebraic equations, we have discussed the bisection method and the Newton method. We have also done several examples using those two techniques. In fact, the Newton method is very scalable for high dimensional systems, and we also looked at all of that. Now, in the remaining time for this topic, we will go through a few more techniques involving nonlinear equations and also learn a few important related concepts. Now, when you're trying to solve for the roots of a single nonlinear algebraic equation, the equation is often of this form. For example, 5x squared plus 2x plus 3 is equal to 0. So this is an example of that, right? The function is a function of x only. Now, sometimes the equations can be given to be on this particular format where p is parameters that are related to the problem. For example, the equation that you may have to solve will look like ax squared plus bx plus c is equal to 0. So yes, x remains the unknown, but a, b, and c in this quadratic equation can be considered as parameters that can change at will. But once you give values for a, b, and c, then this problem reduces to the original problem. But in this particular case, you know that the values of x that you get that satisfy that equation depends on the values of a, b, and c. Just like in the top equation, the answers you get for this quadratic equation would depend on these numbers, right? So this is a specific case of this. Once the parameters are fixed, this becomes that. Nonlinear equations, even a single simple nonlinear equation, has some very interesting characteristics. Let me illustrate that through these four panel figures. On the top left, the function is f of x is equal to sine x. So we are trying to solve for sine of x equals 0 because we are trying to solve for f of x is equal to 0. And we know that x is equal to 0, x is equal to pi, x is equal to 2 pi, x is equal to minus pi, minus 2 pi, etc. are solutions of this equation. So this very simple nonlinear equation has infinite number of roots. So that is why the function, when you sketch the function, it cuts the x-axis at these multiple points, at 0 and at pi, at 2 pi, at 3 pi, minus 2 pi, minus 3 pi, etc. So a nonlinear equation can have infinitely many solutions. If you look at the panel B, it's a third order polynomial in x. So the third order polynomial should have 3 roots. And if you try to compute the roots for this using, for example, the roots command in MATLAB, you will find that the roots are minus 3, minus 2, and 1. That means x is equal to minus 3, x is equal to minus 2, and x is equal to 1 satisfy f of x is equal to 0. So in this particular case, yes, the 3 roots are there. The 3 roots are all real roots, and then they are all distinct roots. Okay, so that is for a third order polynomial. In panel C, we consider another third order polynomial, nothing very different from what you saw in panel B. But if you look at the roots of this third order polynomial, yes, it has 3 roots. But interestingly, what you see is the root at x is equal to minus 2 is repeated. That means it occurs twice. That means it is multiplicity of roots at x is equal to minus 2. So there are 3 roots at minus 2, and 1. So this is the 2 roots at minus 2. This is the root at 1. So again, in this case, 3 roots, 3 real roots, but 2 of them are identical. And the identical roots or the multiplicity of roots at x is equal to minus 2 occurs because the function goes to 0 at x is equal to minus 2, that's fine. But if you take the derivative of the function, if you take f dash of x, that will be equal to 3x squared plus 6x. And if you put x is equal to minus 2, you will get 12 plus minus 12 there. So which will make it at x is equal to minus 2, the function as well as its derivative goes to 0. So the derivative going to 0 is a reason to suspect multiplicity of the root. Okay, so the function, right, what happens is if you plot the function, it just grazes the x-axis there. All right, at that point it just touches and grazes the x-axis, leading to this multiplicity of roots. Whereas at this point, if you look at it, it cuts the x-axis, right? Here it cuts the x-axis, cuts the x-axis, cuts the x-axis, etc. So this is interesting thing that you see in panel C, where some roots can be repeated. Now, if you take another third order polynomial that is given in panel D, what you see is if you draw this function f of x in the vertical axis, as you have done in the other panels, and x in the horizontal axis, so this is x, this is f of x, if you sketch it, you will see that the function cuts the x-axis at only one point, which is at x is equal to 1. You do not see the other two roots at all, like you saw in panels B and C. This is a third order polynomial. So what are the other two roots? Those roots are complex roots. So when you plot it in this way, for x values being real, you will not see those two roots. So in fact, those two roots are complex conjugate roots that you will see. So the point is, even a third order polynomial may not have all the roots to be real roots. And real roots are often important for engineering calculations, right? Because we live in the real world and not in an imaginary world, all right? So this is the interesting stuff about nonlinear algebraic equations, and we see this behavior with simple single nonlinear algebraic equations. The issues before us are, first of all, does a solution exist? We do not know. How many solutions, right? Whether it has infinitely many solutions, or does it have 18 solutions or 3 solutions, we would not know. For polynomials, we can say, yes, the number of solutions will equal the order of the polynomial. But how many real roots? We cannot say, even in that case. Even for polynomials, we cannot say how many roots are real, how many roots are complex, or the roots simple roots or multiple roots. We cannot say any of these things a priori. For linear systems, it was pretty easy. But for nonlinear systems, there are many, many issues. And interestingly, we live in a real world, but the behavior of many systems that is of interest to engineers are nonlinear systems, right? They exhibit certain amount of nonlinear behavior or severe nonlinear behavior. So it is very important for us to learn the characteristics of nonlinear systems and to solve systems involving nonlinear algebraic equations or nonlinear differential equations or nonlinear partial differential equations. Despite the fact that I said there are very interesting challenges in the context of nonlinear systems, there are some clues that people have found out. For example, the number of roots of a polynomial equals the degree of the polynomial. Only thing is that the roots can be real or can be complex. All right, so that's one thing. The other clue is that if all the coefficients of a polynomial are real, then any complex root must occur in pairs. That means the complex root will occur as complex conjugates. For example, if you had 6x to the power of 4 plus 5x cubed minus 3x squared plus 2x minus 1 equals 0, you can safely say this will have 4 roots. And if the roots are complex, then the complex roots will always occur in pairs. That means there will always be roots that are complex conjugates. It means if one root is a plus bi, where a and b are numbers, the other root will be a minus bi. This is what is meant by complex conjugates. All right. We cannot say much about a polynomial which has complex coefficients. So everything else is the same. Let's say this equation has this coefficient for x to the power of 4 as a complex number. So in that case, this statement does not make any commitment to that. Now, the third clue is you check the value of the function at x1 and at x2, two different points. That means you find out f of x1 and f of x2. If f of x1 and f of x2 are of the opposite sign, then there must be an odd number of roots in that region between x1 and x2. So if you take this function, right, x1 and x2 are here, and you evaluate the function at x1, you get a positive value. You evaluate the function at x2, you get a negative value. Let's say this is the 0 value in the y-axis. So the function should be like this. So it cuts the x-axis at one point, or the function can be like this, in which case it cuts at 3 points, etc. So that is what this part means, right? So this should be off roots. And if f of x1 and f of x2 have the same sign, then there must be an even number of roots, right? Either 0 root or 2 roots or 4 roots, etc. So this is x1 and x2. So this is, let's say, x1, this is x2. If you evaluate the function here, you get f of x1. If you evaluate the function here, you get f of x2. Now both are positive above the horizontal axis. So both values of the function f of x1 and f of x2 turn out to be positive. So in this case, the function's behavior could be like this. So that means there are no roots within this region x1, x2. Or the function could behave like this, in which case it has 2 roots, etc. Right? So you can see the validity in this particular statement. In any region where the derivative of the function has a uniform sign, that means it is positive or negative, there can be no more than one real root for the equation f of x is equal to 0. Right? So let's take this region, and in this region, let's say the function has positive slope. Let's say the function is like this. So in this case, I've sketched a function with a positive slope. So this is f of x, and it always looks upwards, right? So it always keeps going upwards. So that's why we say that the function has a derivative that is of the same sign. So if you draw a tangent here, the tangent will be like this with a positive slope. If you draw a tangent here, it will have a tangent like this. Again, it has positive slope, but a different slope, but it is positive. So when f dash of x in this illustration, as you can probably see, this is x1 and this is x2, and within this region the function, let's say, is like this, then f of x is only positive, therefore it can have only one real root there in this domain x1, x2. It cannot have more than one root. It cannot have something like this, right? Because if you take the second curve here, the slope is positive because it always goes upward, but in this region the slope is negative, right? And in this region the slope is positive. So the uniform sign condition is violated. So if the derivative has a uniform sign, then that domain, that part of the region will have only one real root. Okay, so the other thing we need to do, and this is what we understood from panel C in the previous slides, you have to examine the value of the derivative at each root. So this becomes quite important, right? Find the value of the derivative at each root. If the value is 0 at any root, this indicates a multiple root. So if the derivative vanishes near the root, then the slope of the function at the root is going to be 0. So derivative and slope are the same. And when that happens, it indicates a multiple root. So if you look at the Newton method, which we have already learned, we know that x new is equal to x old minus f of x old divided by f dash of x old. And if you have a multiple root, right, if you have a system with multiple root, that means the same value of x repeats, right, then we have seen that the derivative will vanish at that point. Not only the function vanishes, but the derivative will also vanish. This poses a problem for the Newton method because the function going to 0 is good. In fact, that is what we are trying to find out. For what value of x will the function become 0? That's what we are trying to find out. So the function will go to 0, that's okay. But if it is a multiple root, what happens is the derivative of the function also goes to 0 at that root, which means you will have a 0 by 0 situation, which will cause trouble for the Newton method. So the Newton method is not very good when we encounter situations with multiplicity of roots. All right, it works very well when we have distinct roots, but when we have multiplicity of the root, then at that point the Newton method can fail, because the Newton method uses the slope information, and that unfortunately occurs in the denominator, and division by 0 is never good, or division by very small number is never good. That is a shortcoming of the Newton method. So at a particular root, if that root is a multiple root, then you're going to have problems with the Newton method. So we have to devise some workarounds for these kinds of situations. Now, if you take a look at a few examples, this is a function. Let's consider that. So it's a third order polynomial. So we know there are going to be 3 roots. We do not know if the 3 roots are going to be real or distinct, etc. But we know there are 3 roots. Now, if you take the derivative of this function, we get this. As we know, for any value of x greater than 0, this derivative is always going to be positive. So in the domain x is equal to 0 to x is equal to infinity, this slope is always going to be positive, which means no more than one real root in the region. Okay, maximum it can have is one real root based on the idea that we discussed here. There can be no more than one real root, right? So that is what this tells us. So from the function, I say there are going to be three roots. From the derivative of the function, I can say in the region x being 0 or positive, this function f of x can have no more than one real root. And if you take f of minus 5, right, if you put x is equal to minus 5 in this value of the function, you get f of x to be minus 36 at x is equal to minus 5. And f of 0 is minus 6, right? If you put x is equal to 0, f of 0 is minus 6. So between minus 5 and 0, what you see is there is no sign change in the function. It is negative at minus 5, it is negative at 0. That means there could be 0 roots or 2 roots in the region between minus 5 and 0. We are not talking about 4 roots, 6 roots, etc. here, because we know the function can have a maximum of 3 roots. So between minus 5 and 0, because there is no sign change in the value of the function, we guess it should have either 0 roots or 2 roots. F of minus 2.5 is 0.875. So we know there is a sign change between x is equal to minus 5 and x is equal to minus 2.5. You can see for minus 5, the function is minus 36, and for x is equal to minus 2.5, the function's value is 0.875. So there is a sign change. Therefore, there is going to be one root between minus 5 and minus 2.5. And if you look at minus 2.5 to 0, again, the sign of the function changes, because at minus 2.5, it is 0.875, and at 0, the function's value is minus 6. So between minus 2.5 and 0, there is going to be one root. So these are the clues that we get by looking at the function, by looking at the derivative of the function, by testing the function at some values, we are able to get all this information. I also tried f of 2 and I got a value like 20. So I know there is going to be one root in the region 0 to 2. That also satisfies this condition, right? Because f of 0 is minus 6, f of 2 is 20, so there is a sign change from minus to plus. So there should be one root between 0 and 2. So there's going to be one root in this interval, there is going to be one root in this interval, there is going to be one root in this interval. If you really solve the problem using bisection method or Newton method, or simply by using roots command in MATLAB, you're going to get the roots to be at x is equal to minus 3, x is equal to minus 2, and x is equal to 1. And this is what our simple analysis was able to tell us, at least for this simple problem. If you take a second example, f of x is equal to x cubed plus 3x squared minus 4 is equal to 0. Again, using the order of the polynomial, we know there are 3 roots. And if you take the derivative, we get 3x squared plus 6x. And for x greater than 0, this is always going to be positive. So we know there is going to be no more than one real root between x is equal to 0 and x is equal to infinity, because the slope always remains positive once you cross x is equal to 0 on the right hand side. And then I just tried f of minus 2. That means I put x is equal to minus 2 in this function, and lo and behold, I got the value of the function to be 0. So I know minus 2 is a root. Then I check the value of the derivative of the function at minus 2. Once you find a root, right, it is always good to check the value of the derivative at the same value to see whether the root is a distinct root or it is repeated root or a multiple root. So I tried f dash of minus 2, and interestingly I got a value 0, which means the root at x is equal to minus 2 is a multiple root. F of 0, right, I tried to find the value of the function at x is equal to 0 and x is equal to 5. So f of 0 turned out to be minus 4 and f of 5 turned out to be 196. So we know there is one root in between 0 and 5. It cannot be 3 roots simply because we know there are 2 roots at x is equal to minus 2. So it has to be only one root. And we already remarked the root at x is equal to minus 2 has multiplicity 2. It's a double root. So the roots are x is equal to minus 2 and x is equal to minus 2 that we got here. And we know there is one root between 0 and 5. So we can try the bisection method or the Newton method with appropriate initial guess to find out this third root. Okay, so that is how we can analyze this function given in example 2. Now let's come to example 3, where we again consider a third order polynomial that's given there. We are trying to find out the values of x that satisfies this equation, f of x is equal to 0. So we know a third order polynomial should have 3 roots. Now if you take the derivative of this function, we get this. And if you look at it, this is always going to be positive for all real x. The derivative does not change sign, because if x is negative, this is going to be positive. Why? Because you're taking squared of x value. So whether x is positive or negative, 3x squared is always going to be positive. So this is going to be positive even for negative x. If you have negative x, this term will be positive because you have a minus 2, and if it is negative x, then negative is going to multiply with negative, making it positive, and 1 is positive. All right, so when x is negative, f dash of x is positive. What if x is positive? When x is positive, please note this will grow faster than this, and you are adding 1 anyway to that. So this function derivative f dash of x will be positive for positive values of x as well. So this statement should make sense to us. F dash of x is always positive for any real value of x. So what does it say? There can be no more than one real root in the region from minus infinity to infinity. And therefore the system should have 2 complex roots, because there are a total of 3 roots. And this tells us that between x is equal to minus infinity and x is equal to plus infinity, that means real values of x, you cannot have more than one root. Therefore, the remaining 2 roots must be complex roots. And since the coefficients of the terms in this polynomial are all real coefficients, the 2 complex roots must be complex conjugates. Now here, I'm going to try the value of the function at x is equal to 0, and I'm going to try the value of the function at x is equal to 2. So f0 turns out to be minus 1, f2 turns out to be 5. So there is going to be one real root between x is equal to 0 and x is equal to 2. And we can find it using bisection method or Newton method, etc. I also tried f1, right? And I found it to be 0. So just by luck, I tried x is equal to 1, and the function went to 0, or the function vanished at x is equal to 1. So x is equal to 1 is a simple real root. So this told us that it is going to be between 0 and 2. This tells us the root in fact is at x is equal to 1. And just for fun, I try to find out the value of the derivative at x is equal to 1 at the root. So when I put the value x is equal to 1 in f dash of x, so I get 3 minus 2 plus 1, which is 2, which is not equal to 0. Therefore, the root at x is equal to 1 is a simple root. There is no multiplicity, right? And there were enough clues that it has to be a simple root even earlier. We have found out that x is equal to 1 is one of the roots. Now, how do I find the other 2 roots? What can I do to do that? One thing is I can try searching in a different domain, or I can start with a different initial guess and see whether the Newton method takes me to a different solution. We looked at it in the context of the adiabatic reactor that we considered, right? So we found out 3 roots for that system. We found out 3 combinations of x and y. That was consistent with the mass and energy balance we wrote for the adiabatic CSTR system. So if you have to find several roots for the nonlinear equation, then we can search in a different domain, or we can start with an initial guess, or we can use something called a deflation technique. Particularly, this is useful for single nonlinear algebraic equations. The idea is simple. Once we have found out one root of the function, let's say the original equation that we are trying to solve is f of x is equal to 0. Let's say we have found out one of the roots at x is equal to r1. So we have found out one of the roots. So what we do in the deflation technique is you modify f, or you deflate f, by creating a new function g of x, which is going to be equal to the original function f of x divided by x minus r1. So we know the value of r1, so you create a new function g of x that is equal to f of x by x minus r1. And now you try to find out the roots of g of x using bisection method or Newton method or anything that you want. So let's say you find out the root, the other root to be x is equal to R2. Basically, the fact that you have divided by x minus R1 will make sure that the solution technique will not take you back to R1 unless there is a multiple root at R1. So g of x, the solution will not go to x is equal to R1, something that we have found out already. So it will not take us there again. It will take you to a different root. Okay, and let's call that root as R2. So we have found out two roots of f of x is equal to 0. Because if f of x is equal to 0, 0 by x minus R1 is also 0. So g of x is equal to 0 also satisfies f of x is equal to 0. So if you have found out a root for g of x is equal to 0, and let's say that root is x is equal to R2, now you have found out two roots of f of x. So now you can create the third function h of x, which is going to be g of x divided by x minus R2, which is nothing but f of x divided by x minus R1 times x minus R2. So now you can solve for h of x is equal to 0 and get the third root, etc., etc. So this is a very interesting idea, which is called the deflation technique, because we deflate the original function by the root that we have found out. And each time the deflated function will take us to a different root. So that's the idea. So if you apply the deflation technique to this problem here, a very simple problem. So we have found out that the root of this function, one of the roots is x is equal to 1. So what I do is I take the function f of x and I divide it by x minus 1, because r1 is like 1. So x minus r1 is x minus 1 in this particular example. So the new function g of x is f of x divided by x minus 1. So this is f of x and this is x minus 1. So this is a simple problem. So we divide this third order polynomial by this first order polynomial analytically, and then we get this. So g of x is going to be x squared plus 1 in this example. So if you set g of x is equal to 0, basically we are saying x squared plus 1 is equal to 0, which means x squared is equal to minus 1, and therefore x should be plus or minus I. So this function f of x is equal to 0, this particular function has three roots. One root is at x is equal to 1. The other two roots are at x is equal to plus I and x3 is equal to minus I, where I is the square root of minus 1, because I squared is minus 1. And you can see this occurs as complex conjugates, because plus I is nothing but 0 plus 1I. Minus I, which is the third root, is at can be written as 0 minus 1I. So these are complex conjugates. And since the coefficients of the third order polynomial are all real, the complex roots appear as complex conjugates. And this has applications in process control, the topic you will see maybe in your second year or in the third year. This has implications for dynamical systems that exhibit oscillatory behavior. So the general methodology for any root finding problem, and you have seen examples of this in the bisection method and in the Newton method, is that we have to provide an initial guess. Sometimes we have to provide one initial guess, for example, for the Newton method, or we provide more initial guesses for the roots. For example, the bisection method, we provide two guesses. And in a method like the Mueller method, which if we have time, we'll cover later, we have to provide three guesses. So always for a root finding algorithm for a nonlinear system or a single nonlinear equation, what you need to do is you have to provide one or more initial guess values for the algorithm to start. For Newton method, you have to give one guess for each unknown in the problem. For bisection method or Mueller method, which are more applicable for single nonlinear algebraic equations, you have to provide two guesses for the bisection method, secant method, regular falsy method, etc. And you have to provide three guesses for method like the Mueller method. And what it does is the algorithm, whichever algorithm we choose, it iterates using some scheme or some formula. It improves the initial guesses. So the iterations proceed until the iterates converge. And we have seen this enough times in the context of bisection method and the Newton method. Or if you have reached a specified number of iterations, then you can stop the iteration. And then what you do is you check if a meaningful result of a desired accuracy has been obtained, right? A meaningful result is important because ultimately, right, we have to make physical decisions on the process. So the mole fraction should be positive and between 0 and 1. All right. So you have to always do sanity check. It is not enough for the solution to be mathematically meaningful. It should also be physically meaningful. So you have to check for both actually. All right. And therefore you should also check if the result of a desired accuracy has been obtained, because you might get a physically meaningful value, but you have to see if the accuracy is good enough for the intended application that you have. All right, that's why we have these tolerances like 10 to the power of minus 8, 10 to the power of minus 12, 10 to the power of minus 15, etc. We don't use a convergence tolerance of 0.01. For hand calculations, that might be enough. But when you're doing computer calculations, you're doing it for a high stake environment. So our accuracy should be at least of the order of 10 to the power minus 8 or 10 to the power minus 12, etc. So if we have got a meaningful result with desired accuracy, then we can stop. But if we have not got a meaningful result, then you have to change your search domain, or you have to try a different initial guess. For example, if I'm using the Newton method and I get a negative value for the mole fraction, we know it may be accurate mathematically, but it is physically not meaningful. Therefore, I will start the Newton method with a different initial guess and see whether I get a meaningful result with the desired accuracy. Same thing for bisection method, etc. And sometimes I may even have to change algorithms. If you see that the technique that you have chosen is not helpful, then you may have to abandon it and look for a more powerful technique or a more suitable technique. All right. For example, in this course, we advocate the use of Newton method, and it works very well on a large range of problems. But there could be some problem in which you're not getting the best out of Newton method. So you have to look at extensions of the Newton method or devise an interesting scheme to solve the problem. So sometimes using a different algorithm beyond what you have learned in this course may be necessary. And commercial tools come with many different algorithms so that you can choose from them. But even there, some of the things may not be working, and that's what leads to research and further improvement of the scope of those software, etc. I'll stop here and catch up with you in another video. Thank you for your time.